Hello everyone, welcome back to the course. So in the last class we have seen some of the examples of how to do the timing analysis or timing calculation. So again we will see some other examples on this timing information, how to calculate those timing information in some circuits. So again you consider another circuit, this one. Here again we are having two flip-flops. In between we are having from this Q to Q path there is this combinational circuit, and the clock is also buffered. That means one buffer is placed between clock A to clock P, right? So at that time this is the clock, original clock, okay, and this is that means clock which is occurring or arriving at this point. So you see there is a difference between the age, because as the buffer has been placed in between these two particular registers, the clock source of these two particular registers. So this is the launch age and this is the capture age. Capture age means as the second clock age of this particular second flip-flop. So that's why the timing checking will be done. Here it will check this hold time, here it will check the corresponding setup time, and in this particular clock age it will also check the hold time, and here it will check the corresponding setup time check. That means each of the age it will check for the setup time as well as hold time check. That means for this particular age, for this particular age it will check the hold check at the first age of the clock 2, and at the second age it will check the setup time, whereas on the second age of this clock 1 it will check the hold time violation here. So again you if another circuit is there which has been passed by, that means there 3 registers are there, so and 2 combinational circuit in between. So at that time there is 2 different basically clock, one is PH1, another one is PH2. So PH1 is connected with this first one and third one, L1 and L3 clock, and PH2 is a different clock which has been connected with L2. Okay, so at that time how this data synchronization can be done, and how basically you can, that means calculate whether there is hold time violation or setup time violation. So you see where this setup time and where there's hold time violation will, that means be covered, that is be mentioned here in this waveform. So I am not going into the details. So whenever if you see, that means if you Google this clock domain crossing, you will get much more information about this kind of circuit, how to synchronize, that means if any hold violation or setup time violation if you are getting, then how to do that, how to tackle all those problems, that you will get the idea from there. Then timing analysis in the design flow. So this I think already I said, under for creating a clock you have to mention create underscore clock with the name, then the period, and then if you are having or if you are using multiple source in your design, so at that time you have to maintain that okay, this clock is the master clock of my design. So another clock that is not mentioned, okay, clock 1 source, clock 2 source, clock 3 source, something like that also you can mention. So group path you can set, then set clock getting clock, so it will select, okay, it will get your, that means it will do the clock getting of your the circuit to your system. Clock getting circuit we do generally for low power design. Then set clock groups, if multiple clocks are available to you. Then set clock latency, network latency, set clock sense. So clock sense, what is clock sense? This basically specify the unitness of a clock signal, either positive or negative. That means it is, that means what is the age, whether that is positive age or negative age, that it sends this comment. You can actually no, okay. So this set underscore clock sense, this says that okay, this is a particular negative age or this is positive age trigger flip-flop or clock. So then set clock transition. So clock transition means this specifies explicitly the rising or falling transition of a clock. This command is typically used before layout when propagated clock cannot be used. The transition time applies to rising or falling transition at the clock pins of sequential devices clocked by the specified clock. So then set clock uncertainty. So what is clock uncertainty? This specifies the uncertainty or the skew characteristic of a single clock or between two different clocks. For a single clock, simple uncertainty is the maximum difference between successive edge with respect to variation away for the nominal arrival times. For two clocks, interclock uncertainty is the maximum difference or skew between occurrence of clock edge with respect to variation away from the nominal arrival time. Set data check also you can do, set disable timing also you can do. Then and then there are several other options too, set driving cell, set fan out load, set ideal latency, that means ideal value for latency, then ideal network, ideal transition time, say input delay, then input transition time, set load. Basically what in design vision we can set some of these particular things manually, okay, sorry, using that means GUI tool. So whenever you are doing that, that means you are already constraining your design. So that means, and that constant we have already in the last demo we have already saved it, what constant we have put. So this constant also you can put, and you can, that means in the design vision, and you can save all these things after synthesis, that means during the synthesis process you can set that means this is the same constant I will use at design compiler, as well as this same constant I will use at this prime time also. Okay, so this constant you have to start with design compiler. So there you set all these things, then that particular constant again it will be used at prime time. So these are the things. So for ideal clocking, so these are the comments you see here, all these things has been happened, that means prompted in DC and DC cell. So set clock latency with respect to rise, set clock latency with respect to fall, set clock uncertainty with respect to setup time, set a clock uncertainty with respect to hold time, then transition with respect to rise, then transition with respect to fall, and all these things, what workload model we used, that thing also can be done. So then design partitioning. So design partitioning, how you can do this design partitioning? Here you see, that means there is a register, here is a logic combinatorial block, this is C1 C2, then it has been passes through a inverter, then again this is the block A, this is block A, this is block B, and in between of them there is a connection with a inverter, they have been connected. So while I will do the partitioning, so at that time it is basically not that much efficient partitioning of the design. Why? Because you see, from this particular register to this particular register, the whole thing is purely combinatorial. So why we are not considering the whole as a logic block? That means not mentioning that okay, this is U1, this is U2, this is a different cell and this is a different cell. So instead of doing that, I am considering only this as U1 and the rest as U2. Or what I can do, I can consider these particular things as a logic one, that means U1, and the rest of the things as U2. But as each of the thing is that okay, at the inside input side there is a logic, then register, then logic, then register, then logic, then register. So there is a regular pattern. So that's why I have to consider these particular things as U1, and the rest things are as U2. So you can do this, you can, that means type this group path create clock by this name. So then again another example, suppose this kind of circuits is there in your hand, so how to create the clock, then how to create the group path, then that means with respect to this clock, then in out, this reg out, all these things you can do. Then this register retiming optimization, how you can do this, that means how the tool do the register retiming automatically, that you can see that. Okay, so suppose here I am having these two registers, so one path is this one and another path is this one, right? So here this slack is in this path, the slack is -1, and here the delay is 1. So and here for this particular path this slack is +15. Okay, so that means the logic which is, that means the corresponding delay for this particular logic, that is minimum than the corresponding logic which are present here in between this. So at that time what he can do, this particular register that will come before this this NAND gate. So if I do that, so at that time what will happen, so one register if I put that, so the delay is basically 1 here, so that delay will come here, that means after this clock, after this register. So at that time what will happen, this will be plus, so that means this one and this one will be, that means it will be just leveled, so here slack will be 0, and this one, as I am borrowing this delay here there by putting this register at the, that means at the input side of this NAND gate. So at that time what will happen, the slack in this particular path, that will become from 1.5 to 0.5. So and as one register, it needs, whenever it comes to the input side, so at that time I need to place a register here and register in this path to maintain the balance. So that's why here I have, though there are only one registers, but there I need to put two registers in the two paths to maintain. So here you see that slack is also met and the corresponding that means the circuit now it can works very fine. So this is the register retiming option. So by calculating the corresponding delays or the slack, basically slack means what, the actual arrival time, the difference between the actual arrival time and the required arrival time. So the difference between them, that is the slack. Okay. So then this clock can be created something like this. Okay, so clock latency, what is clock latency? What I said, that from the clock source pin to the corresponding pins where it has been connected. Okay, so this particular time is how much time it is taking from the clock pin to the pins where this clock element is connected. So this is known as the clock latency. Okay. So then if the clock has been, it is not that only to one particular register or to one particular that means sequential element the clock is connected, it may be connected all the registers which are that means there in your design. So at that time, if in this path it has also passed through a buffer and it has also passed through a buffer, so the difference between these two, that means that is known as the clock uncertainty. So here you see this is the, that means ideal clock, this one at this particular point, then at the register pin the clock will be something like this. Okay, so this is the latency. Okay, and then this setup time and hold time will be there, and the difference between the edge, that means it is not that all the pulse or the clock connected here and the clock connected here, that will be same. Why it will not be same? Because it is traversing lesser path than the second flip flop. So that's why there will be a change in this particular edge. So this difference is known as the clock uncertainty. Then clock latency, it is already mentioned, and how to mention this clock latency. So the first you have to say that okay, propagated clocks, then set clock latency with respect to rise is 1.2 and clock latency with respect to fall is 0.09 and with the pin of this clock. So then again we can set the source latency. How you can do this source latency? By mentioning this, that set clock latency is 1.5 minus source early and 2.5 is the late. So this is the clock source. Whenever it says that early is 1.5, so after 1.5 this edge will occur. So at that time this is the corresponding that means early clock signal, and late clock signal is 2.5 nanosecond later. So 2.5 nanosecond. So here you see the corresponding setup and the corresponding hold that is mentioned here. That means what is this hold? That means the time which is for this particular early, this is the setup and this is the hold. Okay. So then clock uncertainty. Clock uncertainty I already discussed, that the difference in the delay of the clock source itself whenever it is connected to different that means blocks. How to set the clock uncertainty? So set underscore clock underscore uncertainty to 5 with respect to clock, which clock I want to set the uncertainty, that is clock A. Set underscore clock uncertainty from clock B to clock A, that I can set. So this basically gives me this uncertainty value, will give me the what is the values of skew. So with respect to hold and setup also you can set. So then what is this ideal clock transition time? By putting this command set underscore clock underscore time with respect to rise or fall, you can set. Okay, so this will be the transition time, that whether that is 0.4 point any values you can set. So after doing that, how to, that means what clock you have created, to check the report on that particular clock. So you just write report underscore clock. So what are the parameters you have set for the clock, that it will listed out. Then multiple clocks, if you are having multiple clocks in your design, so at that time you have to set the false path, and if the circuit is designed to use only one clock at a time everywhere, you can disable analysis of multiple clocks by setting the following variables, that is shape underscore app underscore where timing enable multiple clocks per edge false. Okay. Then synchronous clock, asynchronous clock, and this exclusive clocks. This is the example of that. Okay. So synchronous clock means one clock source that is connected to every that means sequential component present within the circuit. Asynchronous means it may be connected with some enabled signal or some other signal. That means if clock getting things are there, so at that time that clock signal should be asynchronous. And then exclusive clocks means we are having two clock sources, then it has been, that means basically multiplexed. Okay, we are having multiplexed clock signal, like for reconfigurable application we need, or multi-mode application we need this kind of things. That means whenever they are supporting different frequencies for at different time, so at that time we need different clock sources to the pin. So at that time you can use this exclusive clocks. So then synchronous clock means only one clock which are having this, that means connected to each of the clock. And how you can set this, whether that clock are exclusive or not. Set clock groups logically exclusive with the group of clock 1 and clock 2. Okay. Then asynchronous clock also you can set by set underscore clock underscore groups minus asynchronous. So again, then how to that means in this particular path, in this particular figure. So all paths clock by clock at the path endpoint are declared to be false, and this false path for the rise edge, or you can set the false path for the fall edge, both you can do. And in this particular example, basically for which A or B or C or path D, what is false path and with respect to what, that you can see as an example. So here you see, that means I am having three resistors which are passes through two buffers. Okay, so then this set false path to then get clock with respect to clock. So clock is this port. Okay, so then in this figure, all the paths clock by clock at the path endpoint are declared to be false. Okay, then this example 2, if I said that okay, set false path rise from this get clocks to clock, then all paths clock by the clock, that means CLK signal at the start point that have the data launched by a rising edge of the source clock are declared to be false. So path A and path D are false. So just like that same example, that means if I set with respect to fall, then at that time what will happen, it will give. Then after setting all these value, you can write this command report underscore timing with respect to rising edge of this clock. If the worst value is 100, so it will show you the what is the reporting that means timing information report for this particular constant. So this is multiple clocks reach at the flip-flops. As I said, these are the example of exclusive clock. So exclusive clock means two clock sources on different time, they will be fed to the corresponding registers. So this false path, I said that okay, it may be that okay, the critical path is different. So here you see that there are basically two paths which are going to input to the output. One path is basically this one, not two paths, another path is this one, then this one, and then this one. So basically this particular path is false path. Why? Because there are in this path there are having another extra, that means inverter is placed here. So that's why the delay will be more than this path to this path. So that means that's why the critical path will be this, not this one, though there is a connection from input to the output for this particular path. So that's why this is known as the false path, because this is not coming into the critical path of the system. So that's why this is false path, and you can set the false path with this comment. So then calculating the maximum and minimum path delay. Okay, no sorry, putting the exception for maximum and minimum path delay. So you can put the, that means okay, set maximum delay will be 12 to this reg A to reg B, or minimum delay will be 2 for reg A to reg B, that you can set. Then this multi-cycle path is, that means for input to the output to pass the logic, it may happen that it is consuming more than 1 clock cycles. Okay, so at that time, that what is the, that means how much clock cycle it is consuming for passing to the input to the output, that means from the launch edge to the capture edge. So that has known as the multi-cycle path. So and it will, as it is consuming the number of clock cycles, so that's why it will be like in the integer part, not the fractional part. Okay, so that's why here you see set multi-cycle path, that is 2 with respect to setup from flip-flop 4 to flip-flop 5. So what is that? Flip-flop 4 to flip-flop 5. So within that, basically here this particular, this is slow logic. So how much clock cycle it requires to complete that has been mentioned by this one, these two. Okay. Then this is the how you can set the multi-cycle path, and if you set the multi-cycle path, so at that time in the waveform how it will be works as that it is shown. These are the examples of that, how to set the multi-cycle path, and what will be the value of multi-cycle path, that is based on the corresponding delay or how many clock cycle the corresponding loss, that means combinatorial logic, is passing through. Then timing path margin that means exception also you can put, so I am not going to the details of that. Exceptions, efficiency. So these exceptions in the order of precedence means this basically applies the exception precedence rule independently on each path, not each comment. That means each of the path you can put that okay, this will be proceed over this path, or this exception will be get the precedent over that particular that means exception comment. So that you can say that you can set basically. So that for false path, what we have seen that okay, we have to set it for this setup time or fall time, or setup time on a hold time, or in some case it is rise time on fall time. So you can put that okay, this exception should be precedent over the other one, that you can set. And then this using prime time you also can calculate the power that means power consumption of the circuit. Okay, so power consumption, power dissipation in CMOS IC, that is basically there are several power consumption occurs. One of that is dynamic switch power. Okay, so dynamic switch power is basically whenever you apply the test vector to the signal and that means you notice that, or you captures the information about how the that means nets or how the gates are basically acting to those vectors, or what are the switching activities happening for that particular test vector. So that you have to store somewhere, and you just give that information to the tool so that it actually calculate the switching based power calculation, which comes under dynamic power consumption. And you will get much more that means detailed information about the power calculation on using prime time that means power analysis tool. So then you have another that means power dissipation, which is short circuit current due to short circuit. That means you will get the power consumption, and then leakage current power source. It is caused by two reasons. One is that reverse bias diode leakage on transistor drains, and the another one is the sub-threshold leakage through the channel to an off transistor or device. Okay, so these are the powers, that means and then I think, and this net switching power is also there. So we have seen some of that means cell internal power is also there whenever you will calculate this power in that means prime time. So we will see this timing analysis and this power analysis. Not power analysis I cannot do here, because for power analysis calculation you have to that means get the information about, after applying the test vector you have to store the switching activity file, and then it has to pass to the tool. Okay, so that it calculates those power calculation accurately, but otherwise it will show you whatever that design compiler has shown the result of on power consumption. The prime time will also give you the same result, because unless and until you are providing the switching information. Okay, so that's why this but now we will use this prime time for getting this information about timing information, and as well as we will try to use this for physical design. Okay, so this is it. Thank you. We will see the prime time demo after this lecture. Thank you.